Ohm's law, to understand Ohm's law, we have to understand current density. Current density is a vector. We use the symbol J. It is a vector, and it is the current per unit area. So it's the amount of charge per second, but it's divided by how much area it's going through. So notice that what we have is current, which is I neva. We divide that by unit area. We just get I nev, or the J nev, right? That's just taking the current equation, dividing it by area. You get the number of charge carriers per unit volume times the charge per charge carrier, the elementary charge, times the drift velocity. So that's current density. It's basically current per unit area. For example, here's an example of this. If this area right there is equal to 0.05 meters squared, and the current passing that point is 20 amps, what is the current density passing through this area right there? Go ahead and figure that out. What's the current density? 20 amps going through that end of that wire, which is 0.05 square meters. That's a pretty big wire. What's the current density? 20 divided by 0.05. Well, let's see, 20 divided by 5 would be 4. 20 divided by 0.5 would be 40. 400, and the units are amps per square meter. 400 amps per square meter. Did I do that right? Yeah. So that means every square meter of that end point right there has 400 amperes going through it. Okay, the other concept we need is conductivity. We use the letter sigma for conductivity. Sigma, conductivity, this is the current density you get per electric field. And in fact, we'll get to this in a minute. This depends on the material. Different materials have different conductivities. You might guess which has more conductivity, a piece of copper or a piece of wood. Copper is a much better conductor. It has higher conductivity. The way I like to look at it, though, is in terms of resistivity. 1 over the conductivity is resistivity. We use the symbol rho for that. Different materials have different resistivities. It is the inverse of conductivity. Which has higher resistivity? Copper or wood? Wood does. Which has more resistivity? 10 square meters of copper or 1 square meter of copper? 10 square meters of copper has more resistivity. 2, 1 square meter of copper has more resistivity. 3, neither of the above. Which has more resistivity? 10 square meters of copper or 1 square meter of copper, or neither? The answer is neither. It depends on the material only. We're going to get to resistance in a minute. That depends on the shape of the material and the size. Resistivity is only dependent on the material. It's dependent, I'll re-emphasize this, it's dependent only on the material. Resistivity or conductivity. Copper has the same resistivity no matter what size it is. So this is actually Ohm's law right here. This right here is, let's see if I can get another color here. This is Ohm's law. J, the current density, is the electric field times the conductivity. Now, I prefer this form of it. So this is the one I like because this looks like the Ohm's law we're used to. The current density is the electric field divided by the resistivity. This looks more like the Ohm's law that we're used to. So this is why I like this version of it, although it's exactly identical to saying this. That is Ohm's law, or that is the same thing as this right here, Ohm's law. Notice that the current density depends on the electric field. It's proportional to it. It's directly related, but it's inversely related to the resistivity. So the more electric field you have, the greater the current density is. Now, only Ohm's law is not a law. There's only certain materials that follow Ohm's law. They're called ohmic materials. Luckily, many, many materials are ohmic. Wires are ohmic. Resistors are ohmic. One thing that is not ohmic, though, is semiconductors. Those do not follow Ohm's law. Neither does a light bulb. An incandescent light bulb its resistivity changes as you pump more current through it. We'll see why momentarily.